Hello, MathQuantum fellows. It is a great pleasure to be speaking with you today about my quantum computing experiences in college. My name is Lucas Papamitsakis, and I'm a rising sophomore at Yale College studying math and statistics. I'm interested in the intersection of quantum computing and machine learning, and while I've been focusing more on the programming implementation of quantum computing algorithms, the multitude of physics concepts embedded into quantum computing has never ceased to capture my curiosity. Rather than a more technical talk about quantum adjacent subjects, I'd like to focus more about what it means to explore quantum computing from the perspective of an undergraduate student, and how learners across the world could gain a clearer grasp of the technology. Entering college last fall came with a flurry of new expectations and responsibilities. But one of the greatest shifts entailed the pace and the depth in which we learn academic content. While my interest in mathematics during high school did give me valuable problem-solving skills via exposure to subjects like linear algebra and multivariable calculus, my mathematical thinking was still in its infancy then. Fortunately, the various lectures from the MathQuantum summer program, from learning about Bloch spheres to Bell's inequalities, were a great gateway into tasting higher level maths and properly set my expectations for the mathematical foundations necessary to better appreciating and understanding quantum computing. My experience with MathQuantum compelled me to focus on theoretical math concepts during my first two academic semesters in college while I honed the programming aspects of quantum computing outside of the classroom. Taking proof-based linear algebra, combinatorics, graph theory, and analysis courses had an immense impact on the rigor and deliberateness on how I approach mathematical concepts, providing me with a wealth of insight into the inner workings of the building blocks of quantum computing. I even remember how my linear algebra class had a brief aside about the utility of spectral decomposition in quantum mechanics with regards to Hermitian operators. It was incredibly fulfilling for me to see the theory within mathematics and physics merge together in class to provide applicable results in quantum computing. Nonetheless, learning these new proof-based methods of approaching mathematical theory in the classroom only took me so far in my quantum computing journey. Thus, I had to supplement the learning process by out of the classroom experiences and plenty of self-studying. One of the ways in which I further solidified my knowledge of quantum computing is through my college's undergraduate quantum computing club, or YUQC, which was pivotal in bridging the theory I learned in my courses with applications of the field. The weekly meetings, which took place at the Yale Quantum Institute, or YQI, among hanging prototypes of old superconductor quantum computers and whiteboards scribbled with matrices and circuits, were intimate and informative, covering all of the theoretical necessities of quantum computing, starting from basic gates and going into complex algorithms. Just like MathQuantum, it was very fulfilling and motivating to learn alongside a small group of peers who were all eager to uncover the mysteries of quantum computing, providing me with a bedrock community to lean on while traversing the technical heavy side of quantum computing. The various project pathways I could choose to work on within the club, from cryptography to error correction, broadened my view of how to use quantum computing in a real world setting. I became compelled to zoom into the already niche community of quantum learners and find a space of peers willing to devote even more time to understanding quantum computing applications, such as by collectively perusing and annotating recent research papers. The project-based meetings within YUQC were complemented by the near weekly YQI lectures of quantum computing scholars and entrepreneurs who are willing to speak about their experiences developing quantum-based technologies and products in areas like chemistry and finance, which played an important role in grounding my learning activities to tangible outcomes achieved by the field's professionals. Another incredible learning experience for me took the form of an annual Yale Community Quantum competition in the fall, with the YUQC mainly focusing on introductory computational theory, and very niche quantum applications. The fall hackathon enabled me to understand the importance of general software development within the realm of quantum computing, which is central for implementing, say, quantum machine learning algorithms. The main goal of the event was for participants to learn IBM's Qiskit language through guided Jupyter notebooks. Uh, First, to implement simple circuits and algorithms programmatically, such as the variational quantum eigensolver, and then understand even more abstract programming concepts like the quantum transpilation pipeline, which is integral to ensuring that circuit and algorithmic instructions for one quantum device can be used by a different quantum device to achieve the same goals while optimizing the outcomes based on the hardware's unique noise. The fast-paced nature of the hackathon, filled with lectures and work session activities, was a ripe learning environment for me, particularly because I had the opportunity to work very closely with a group of friends during the hackathon. Diving deep into the translation process, we learned how high-level quantum circuits are mapped, optimized, and scheduled for execution on quantum hardware, gaining practical insight into path managers, qubit mapping strategies, and gate cancellation techniques. Collaboration was key during our final project, in which we combined our diverse backgrounds in math, physics, and computer science to tackle the broad challenge of implementing a quantum-related algorithm of our choice to solve any real-world problem. We decided to design and implement a quantum-based neural network for handwritten digit technology uh, using the built-in Qiskit library, which entailed encoding image data in the quantum states, training variational circuits using gradient-based optimizers, and evaluating the model's performance via simulation. This project not only deepened my own understanding of quantum machine learning in Qiskit, but also underscored the power of interdisciplinary teamwork in overcoming the complexities of quantum software development. As for any subject, everyone has a different path toward learning quantum computing. Some people may just be interested in the math or physics or programming before discovering the bountiful contributions each subject has toward the field of quantum computing. In my case, it was the math that brought me closer to appreciate the power of quantum. With technical aspects of quantum computing being a daunting challenge for many learners, having a community of learners and collaborators in the field of quantum computing goes a very long way for motivating and building one's knowledge of the field in an engaging manner. Learning through group sessions and projects in a generally low stakes environment is a good complement to more formal classroom methods of learning and enables students interested in the field to dive deeper into the subject than most courses. Hackathons, as I've already mentioned, are also an important learning opportunity for any student interested in quantum computing. While they're very fast-paced and intense, such events compel us to absorb and process large amounts of information, while exposing us to a multitude of different applications of quantum computing, which is bound to catch our interest in some aspect of the field and ignite future project endeavors. The team aspect of hackathons plays an important role in getting a feel for how collaboration takes hold in quantum computing, giving students a comprehensive understanding of the hard and soft skill aspects needed in order to thrive in the field. Thank you so much for tuning into my talk on quantum experiences in the undergraduate setting. I really hope you all gained a unique perspective of what it's like to study quantum computing in the age of the subject's proliferation. To all of the undergrads in the audience, stay active in the quantum community and keep up the great work that feeds your curiosity and collaboration. To the researchers and professors, thank you for making a genuine effort to mentor us undergrads and guide us towards our aspirations in quantum computing. If you have any questions or comments, you can contact me at my school email. I wish you all the best during the remainder of this wonderful symposium.